So I'll look at just a couple problems regarding triple integrals and cylindrical coordinates. So this one, it says the paraboloid, bounded by the paraboloid x equals 5y squared plus 5z squared, and x equals 5. So we know that's a paraboloid, and that's going to, since it's the linear is x equals the sum of a y squared and a z squared, that's going to be opening in the positive x direction. And this one hasn't been translated, so its vertex is at the origin. Like this. Okay, so it's open. It's a paraboloid opening up on the x-axis, and then the plane x equals 5 is the vertical plane 5 units in front of the screen, and so that could be where I drew this circle, say. And then then we're looking at the solid, right? This is the solid bounded by the paraboloid and x equals 5, and so they want us to evaluate this triple integral, and so they don't tell us what order to use. We can use any order we want, so we want to choose strategically. We want the kind of the easiest or the most efficient. So what do we think? Do we want to have our surface to surface inside integral be z, bottom to top, or x, back to front, or y, left to right?
Back to front.
Yeah, so definitely back to front. If you do bottom to top or left to right, then you're splitting this paraboloid into two, and you're having to solve for z or y, and you have square roots, and then you have like the negative square root and the positive square root. This is like kind of undesirable direction to go. But if we do dx first, and we shoot from back to front, then the back is going to be, we've got it right there, nothing to solve for, the paraboloid. The arrows will head in, and then through the solid, and they'll head out, x equals 5. And that will be the front. And so that's going to be the easiest kind of approach for that. So then we'll have 5y squared plus 5z squared is the back. From back to front, x equals 5. And then x, and then we're going to have dx. And then the question is, outside double integral, what makes the most sense for the outside double integral here?
Use polar coordinates?
Yeah, for sure, because so when we project this thing in the YZ plane, we're going to get basically this disk right here. This is the biggest that this thing gets, right? It's like kind of the widest profile. So when you project it into the YZ plane, that's the circle that you get as the projection. Back there on the YZ plane. And so because that's a disk, and it ends up being a disk of radius 1, because if you set 5.
What does that mean? You do it 3 times.
Hey Jay, your microphone is on. Jay McGrath, your microphone is on. So x equals 5. Solving this makes the actually makes the disk of radius 1. So we're going to do our r dr d theta. And so r is going to go from 0 to 1. Theta is going to go from 0 to 2 pi. That's the unit disk. And then this will be 5r squared, right? Because now we're in polar coordinates in the yz plane. So y equals r cosine theta, and z equals r sine theta. And y squared plus z squared equals r squared. And that's what I'm using right here. So really what we have here is like cylindrical coordinates, but rotated in on the x-axis, right? So that your x-axis is your first variable, and then your r and theta is in the yz plane. So this is really no different than cylindrical coordinates, except that we're just rotating from the z-axis to the x-axis. Okay, so questions on that one? Okay, so another one I want to talk about is something that we saw back in double integrals. You had this ice cream cone problem. Remember this in double integrals? Where we had, say, a sphere, and I'll just say radius 4. So x squared. Okay, and then you had a cone, which is, that cone is z squared, it's x squared plus y squared, or z equals square root of x squared plus y squared. That's the cone. And you were charged to find or integrate over this solid with a double integral, or find the volume. I think it was you were charged to find the volume, right? You're going to find the volume of this. And so now that we have cylindrical coordinates, so this thing looks like this, something like that. So now this is really suited for cylindrical coordinates. I don't think there's one in this actual set, but I just want to talk about this as a cylindrical coordinates problem, because we would have so this is a new problem. No, this is not. I'm just using the space on the screen, so there we go. Okay, so the new problem. So we know, say we wanted the volume of the ice cream cone. So we know we'd integrate 1, and then we would have, if we're doing cylindrical, it'd be dz times r dr d theta. So z would be bottom surface to top surface. So what's our bottom surface then?
X squared plus y squared.
Yeah, it'd be the cone. So actually be square root of, right? So it'd be z equals that. And then the top would be the sphere. So the bottom is the cone, the top is the sphere, again solving for z. But now we have to get those in r and theta. So what is the square root of x squared plus y squared in terms of r and theta?
Just r.
Just r, right? So notice that this cone, z equals the square root of x squared plus y squared, is equivalent to z equals r. So z equals r, meaning the distance you are away from the z-axis is the same as the distance you are up. Every point in space like that is this cone, if you think about it. So no matter where you are from the xy plane, if the distance you go up is the same as the distance you go out from the z-axis, then that's every point on that cone. All right, and then similarly, what about the top of the sphere here? So in terms of r and theta?
Square root of 16 minus r squared.
That's right. So minus x squared minus y squared is minus r squared. So that's z equals that as an equation of the sphere. And then what are we going to have? We need to project. So for our polar part of the cylindrical coordinates, we need to project this thing. So at its widest point, it's this circle right here. So we're going to project that thing down into the polar plane or the horizontal plane. And that projection at the widest point comes from the intersection of the sphere and the cone. So we're going to bring these together to get only x and y. Right? So if we bring these together to get only x and y, we'll get the projection of the intersection in the xy plane. So I can just replace z squared with another x squared plus y squared. So this thing will be 2x squared plus 2y squared equals 16. Again, I'm substituting x squared plus y squared in for z squared for the cone. And so then I get x squared plus y squared equals 8. And my radius is square root of 8. So then r goes from, so it's the disk, right? So the projection of this solid into the xy plane is all the points on the disk. So I'm going to go from 0 out to radical 8, and then theta around from 0 to 2 pi. So notice, so this, because we're doing 1 dv, right? This whole thing is our dv in cylindrical coordinates. Since we're integrating 1 dv, that will get the volume of the solid that we're integrating over, which is the limits of integration. But notice what happens. When you do the first integral, your antiderivative will be z, and so then it'll be this minus this. So it would be square root of 16 minus r squared minus r will be the new integrand, and it'll be a double integral. Well, that would have been the double integral you got when you were doing it as a double integral, because to get volume, you do top surface minus the bottom surface to get everything in between. So when you set up that double integral, you would have done surface top minus, or z top minus z bottom, and then r d theta would give the volume between, right? Double integrals give net volume. If you do top surface minus bottom surface, you get the volume in between two surfaces. Well, that's exactly the double integral you get when you start this triple integral, right? After you do the first step, here's z top, here's z bottom. It's exactly the same thing that you get when you set up the double integral. Okay, questions on that? Okay, so today we're going to start, we've done triple integrals in rectangular coordinates, and then cylindrical coordinates. And we said cylindrical coordinates was hardly a jump to be anything new at all, right? We already knew what z was. Z is our up and down coordinate, or vertical coordinate. And then we just, instead of doing either dx dy, we made it polar. And so z plus polar is cylindrical coordinates, and that was all things we'd seen before, so it was hardly a jump at all, or really nothing new. So what we're going to do today is called spherical coordinates, which is a whole new ball game. This is totally different, and it's going to take some time to build here from the ground up. So let's do that. Okay. So cylindrical coordinates lay on this thing. So cylindrical coordinates, the three coordinates in cylindrical coordinates are rho, theta, and phi. I have them listed right here. So rho is the distance from the origin now, truly the origin in R3. Always the distance to that point, right there. Distance from the origin. Okay, remember what R was. What was R? R was not the distance from the origin, but the distance from what?
The z plane, or z axis.
The z-axis, right? So r is a horizontal distance from the z-axis to your point. Okay, so it's kind of like radius in the plane. Okay, but it's the distance from the z-axis to your point. All right. So theta, and so rho is going to be greater than or equal to 0. So we're not going to consider negative rho values. Rho equals 0 is the origin, and then as you move away from the origin, whatever distance you go, that's rho. Okay, so then theta is the standard trig polar integral. No, not integral, angle measure. Okay, and what are the possible? So our convention for theta is going to be 0 to 2 pi. That's standard. So theta is not anything new. It's still the standard trig angle swept counterclockwise from the x-axis. Okay, phi is our last coordinate in spherical coordinates. This is different. Something new here. And so to talk about phi, I want to set an angle theta first. Okay, so I'm going to come up here. So if I think about theta like this here, so here's theta equals 0, right? Positive x-axis, sweeping positive, theta equals pi over 2. And then through the second quadrant, back to theta equals pi. Through the third quadrant to theta equals 3 pi over 2. Through the fourth quadrant, back to 2 pi. Standard stuff, right? So this is the same theta you've been dealing with all the way back to trigonometry when you're learning cosine and sine. All right, so here's this gray planish thing, this gray kind of half disk, is indicating some angle of theta. So I'll make it something like pi over 3. So here's theta of pi over 3, something like that. And so what phi is, the angle phi, is in the direction of theta, in that direction. It's the angle tipped down from the positive z-axis. See that? So this is 0. This is about pi over 4. Pi over 3 is around here. So what is the so when that terminal side becomes horizontal like this, what angle of phi is that?
Pi over 2.
That's not pi over 2 or 90 degrees. And then below the xy plane are angles greater than pi over 2. So here's like 2 pi over 3, 3 pi over 4, 5 pi over 6. And what angle would be then the negative z-axis?
Pi.
That would be pi. So the angle phi is the angle tipped down from the positive z-axis in the direction of theta.
So this is replacing a z, essentially?
No, it's not really. Phi doesn't really replace any particular other coordinates. It's just that rho, theta, and phi together are a new way to specify points in space.
Okay.
But there's not really a matching between phi and a previous coordinate or rho and a previous coordinate. They're like totally new animals.
Does phi will get bigger than pi?
No, it will not. So its range will be from 0 to pi only.
Thank you.
Yep. Because what would happen? So like if you kept going, if phi kept increasing past pi, well, if it kept increasing, then it would be really an angle less than pi for a different theta. Do you see that? If it kept going, it would be like over here now. But that would be for a different theta, that would be an angle less than pi on the way down this way. And so that's the way we want to think of it, only up to pi. So is the angle tip down from the positive z-axis, but in the direction of theta. And so phi can be between 0, positive z-axis, and pi, the negative z-axis. So if my theta, say, was pi over 2, so right now it's about pi over 3. So I'm going to make a pi over 2, just for an example here. Something like there it is. Okay, so there's theta equals pi over 2. And so here's my phi angles, right? So phi of 0, pi over 6, pi over 3, pi over 2, etc., down to pi. Now, if I were to change the angle theta to 3 pi over 2, something like that, some students have thought in the past that this would be like negative phi's now, negative angles. No. So phi is always in the direction, it's a positive angle in the direction of theta. So now we're just going to tip down to the left because theta is in the negative y-axis. Basically, theta is the direction of the negative y-axis. So positive, it's still positive phi, it's just tipped down in the direction of theta. So these are still positive values of phi. You know, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi. So it's not, phi is not positive in one direction and negative tipping in the opposite direction. It's always positive in the direction of theta. Whatever theta direction theta points, phi will tip down in that plane of theta and go from 0 to positive pi. Okay, does that make sense? So you see how we can get all points in space this way. So first pick a theta. Oh, wait, and so, sorry, we didn't get to the last part. So let's go back to, say, pi over 3. So here's pi, like about pi over 3. So we pick our angle theta. I pick pi over 3. Pick our angle phi. Say I'll pick whatever 0.785 is. So this is 0.785 radians. So let me draw that in here. So this is theta equals 1.13 radians. This is phi tipped down from z of 0.785 radians. And now, so then our potential points could be along that ray shooting out at theta equals 1.13, phi equals 0.75, and then rho gives me my distance from the origin. So let's say right there, that's rho of, oh, let's do that one. So now that's a distance, that's rho of 1.775. In other words, the distance from the origin out 1.775 in the direction of phi and theta gives me this point right here. So this is 1.775 is rho. 1.13 is theta. 0.785 is phi. The way that I think makes the most sense to plot points is theta. So plotting theta first, then phi, then rho. Get that gray angle in the right way, tip down, and then see how far out you're going to go in that direction then. But the way that they're listed is conventionally is rho theta phi. Okay, questions on plotting points? Okay, so now we've got rectangular coordinates, cylindrical coordinates, and spherical coordinates, 3 coordinate systems that are all coincide, right? They all have this origin. They all are based on the x-axis, y-axis, and z-axis, and so we need to know how to transition back and forth between these coordinate systems. So let's plot one more point. Let's just have you practice one more point, and then we'll do that. So how about the point 2.5 and 7 pi over 6, 3 pi over 4. So could you plot this point in spherical coordinates? Could you find where that is? Right there. So give it a chance here, give it a shot while I do a little erasing. And could you plot that point in R3, if those are spherical coordinates? Okay, so first we're going to look at, so let's just put here. So first we're going to say where is 7 pi over 6 for theta? I prefer doing theta first.
Oh, I know.
So what quadrant is 7 pi over 6? Anybody? First, second, third?
It's in the second quadrant.
7 pi over 6 is in the second. Everyone agree with that?
Yeah.
I think it's in the third. I'm not sure.
Yeah, it's pi. So third, because pi is pi is halfway between second and third. 7 pi over 6 is going to be a little bit greater than pi.
Right.
So something like that. Pretty close to, yeah, right around there. Maybe a little bit further. All right, so here is just a little bit, it's the angle a little bit past pi. Something like that, okay. And then 3 pi over 4 for phi. So where will that be? Is that going to be above, pointing up above the xy plane or down below?
Below.
Below, right? It's going to split the horizontal plane and the z-axis in half, 3 pi over 4. 3/4, 9/4. A little bit further, maybe. Yeah. Something like that. So we're at 5 pi over 6 for theta, which is just past pi. And then in that direction, we tipped down. In that direction, we tipped down from the positive z-axis 3/4 of the way to the negative z-axis, right? So let's just draw those there. And then this that's tipped down from the z-axis 3/4 of the way to the negative z-axis. And this is supposed to be horizontal. So show that any better.
Why is it 5 pi over 6, not 7 pi over 6?
It is 7 pi over 6. Sorry, I just wrote it wrong. Thank you. Good. Gee whiz. Oh, that one's right. Okay, so let's see if we can do this better again. So it'd be like starting here. That's better. So it's like horizontal, right? So that's swept around to 7 pi over 6, and then 3 pi over 4. This isn't great. something like that. And then our distance of 2.5 from the origin. Rho is 2.5. Close enough. So then in that direction, theta equals 7 pi over 6, phi equals 3 pi over 4, go a distance of 2.55 from the origin, that gives us a point. So now what we want to do is figure out what would the x, y, and z coordinates of that point be. Well, that's not immediately apparent. It's not, we have to figure that out, okay? And that's what we're going to do next. But that's going to take a little work. Okay, questions on just the basics of like what the coordinates are and plotting points and spherical coordinates? Any questions? All right, so let's, like I said, let's talk about transitioning between coordinate systems or figuring out what.
Question, you start measuring your theta from the positive x-axis?
Same theta, same standard trig polar angle we've always done, yep. So yeah, it's the standard trig and polar theta. No change there. Okay, so I'm going to turn off this. And I'm going to get this. And then it's. And let's tip down a little bit more, maybe. That's good. Okay, right there. So this is out in the first octant, right? So we've got a theta less than pi over 2 and a phi less than pi over 2. So this point is in the first octant. And I want to label, we're going to label all the coordinates. So first of all, what's the coordinate that's the distance from here to here? What's that coordinate?
Rho.
That's rho. That's the new one we learned today. That's the distance from the origin to the point. Okay? And what is r? How would I define r for this point? What is r? R is defined how?
The r from cylindrical coordinates.
Yes. And polar coordinates. Yep, same r.
Okay. It'd be like sine phi or something? Cosine phi.
No, I don't. I'm not saying to do any math relationships. I just want to know what it is. How is r defined?
It's like the radius on the horizontal plane.
Yeah, distance to the z-axis.
Yeah.
That was a really bad line. So the distance to the z-axis. So I want to do that down in the. I want to rather than do it up here and floating. I want to do that down in the xy. So what I want to do is I want to drop a vertical here. And what would that? So if this made it to the horizontal plane, then what is that a coordinate right there? What's that coordinate?
Z.
Someone wants z. Agree with that?
Yes.
That would be z. And now from here, what would be r? How would I do the r? Where would I go?
Distance from the origin.
Yeah, so if I'm in the xy plane, I can draw that to the origin, right? So it's this. That's my r. All right, and then what about x and y, right? So what about the x and y coordinates? What is this coordinate right here?
Y.
That's my y coordinate, which makes this one my x. And this is a right angle, right?
Isn't
And
your
where-
convention x going in? Oh, I got it mixed up.
And where is my right angle in this triangle? Exhibit A, B, or C?
C.
C. Okay, where is angle theta? Where's angle theta?
X and R.
Between x and r, good. And where's my angle phi?
Between the z-axis and rho.
That's right. And where is phi in this? So we got a vertical right triangle. See this? This is a right triangle that's vertical. That phi shows up again in that triangle. Is it exhibit A or exhibit B?
B.
Yeah, alternate interior angles, right? If this is phi, this is parallel. These are parallel lines here, so this would be phi also. Okay, so let's talk about x, y, and z in cylindrical and then spherical coordinates. Before we do that, we have to get what r is. What is r now in our new vertical triangle here? So this vertical triangle relates to spherical coordinates, right? What is r in that triangle? What relationship does it have to rho, phi, and z?
Rho times sine of phi equals r.
He wants r to be rho sine phi. Rho is our hypotenuse. R is the opposite side from phi, so that's it. So r is defined as rho sine phi from this vertical triangle, right? Because this is the opposite side to phi. Rho is the hypotenuse. And so we know in cylindrical coordinates, x is what? Looking at this, so cylindrical coordinates, we can get x and y down here in this horizontal triangle. X is
R cosine theta.
Yep. We've already done that. And y is our sine theta. So now, to get spherical coordinates, cosine theta is fine. Theta is still in spherical coordinates, but r is not spherical coordinates. So what is r in spherical coordinates?
Rho sine phi.
Yeah, that's what we found here, right? So r is our rho sine phi from this triangle. So I can replace r with rho sine phi. And so this is what x is in spherical coordinates. It's rho sine phi cosine theta. Similarly, y is r sine theta. Sine theta is fine in spherical. We just need to replace r with rho sine phi again. So rho sine phi sine theta. What is z in cylindrical coordinates?
Rho cosine phi.
No, in cylindrical coordinates.
My bad.
That's okay.
Still just Z.
Still z, right? It's the same coordinate, right? Now spherical coordinates. So someone answered, look, to get z in spherical coordinates, we're going to look at z as part of this vertical triangle. And so what is z? You can say it again now.
Rho cosine phi.
Yeah, so z is the adjacent side to phi. Same hypotenuse. So rho cosine phi. Okay, good so far? Okay, what else do we need now? Now we also know, so this is how r relates to spherical coordinates. How does it relate to, so we could do this, let's do this. So in spherical, so we could kind of keep the same thing going on here. So in spherical r, and we said r was rho sine phi in spherical coordinates. What is r in rectangular coordinates?
Square root of y squared plus x squared.
Yep. Very good. So we know r is rho sine phi, r is also square root of x squared plus y squared. Actually, r is kind of the bridge between spherical and cylindrical coordinates. right? Because r shares the side in the horizontal triangle and the vertical triangle. Okay, next. We know in theta. What is theta in rectangular coordinates? How do we solve for theta in rectangular coordinates? Remember what we do to get this angle measure?
Is it arctan y over x?
Mm-hmm. Arctan y over x. Remember that if your angle is in second, third, or fourth quadrant, you'll have to make an adjustment. Arctan will always give an angle between negative pi over 2 and pi over 2. So for angles, we did an example like this Friday. For any angle in the second, third, or fourth quadrant, like greater than pi over 2, this will not give you the angle directly. You have to make an adjustment. You have to figure out what it is. Okay, and so what's left here? So how about rho? Rho, so theta is also theta in spherical coordinates. What about rho in spherical coordinates? If rho is in spherical, what is that in cylindrical coordinates? There. So we can get in cylindrical coordinates by looking at this triangle. Rho, how does it relate to r and z? Rho, r, and z.
R squared plus Z squared equals rho squared.
Mm-hmm. So we could actually just write that. Let's just write rho squared, and that's r squared plus z squared. That would be cylindrical coordinates. What about rectangular coordinates then?
X squared plus y squared plus z squared
Mm-hmm.
squared.
Now notice something. X squared plus y squared plus z squared equals rho squared. What is that?
The formula for a sphere.
This is a sphere centered where?
At the origin.
Centered at 0, 0, 0 with radius
Rho.
rho. So look, if rho is the distance away from the origin, if you have a constant value of rho, so it's every point that's the same distance away from the origin, well, that's a sphere. That's considering rho to be the radius of a sphere. And we know, so we've got that relationship that matches the equation of a sphere here. Rho squared equals x squared plus y squared plus z squared. Thus, spherical coordinates. Spherical coordinates is based on constant values of rho, gives you spheres centered at the origin. So think of shells, right? Think of shells of different radius. That's the way to think of rho as a coordinate. Not just in one direction, but like in all directions. So like the rho axis, kind of per se, would be like concentric spheres coming out from the origin. Different values of rho. Okay, finally, some phi values. So phi, what would phi equal in? So phi, notice that phi is from 0 to pi. So which arc, do you know which arc trig function has a range of 0 to pi? Arc cosine. Arc cosine gives an angle measure between 0 and pi. Arc sine and arc tangent give an angle measure between negative pi over 2 and pi over 2. So because arc cosine gives an angle between 0 and pi, it makes the most sense to define phi in terms of arc cosine. Because then it'll spit out an angle in the range of phi. So arc cosine of what? Arc cosine, so what's the cosine relationship to phi here?
Rho over z.
So it's going to be, is it hypotenuse over adjacent or adjacent over hypotenuse?
Z over rho.
Yeah, z over rho, right? So the cosine of phi is adjacent over hypotenuse. So we want our cosine, and then we could, to make it all in terms of rectangular coordinates, we could do our cosine of z over
root x squared plus y squared plus z squared.
That's it. And there it is. So there's our formulas. Cylindrical to rectangular, cylindrical, spherical, and then a couple angle or formulas for phi, which I couldn't get. I didn't have room down here. But it would be phi over here in spherical coordinates equals arc cosine of z over radical. Radical would be in rectangular coordinates. Any questions? So, yes, these formulas are for using and for transforming between coordinate systems, but watch out for just blindly plugging into the formulas and expecting to get the right answers every time. As we've seen with these trig functions, especially inverse trig functions, you have to plot the point, make sure the numbers you're getting are making sense. So always plot the point, think about it, think about the location of the point, and that the values of the coordinates are making sense. Not just, oh, I used the formula and I got the wrong answer, right? So think about it, like draw a picture, work it out. You know, make sure the location of the point agrees with what its coordinates are, okay? So it's not just a mindless plugging into formulas. All right, I'm gonna do one more thing, and the quiz, like I said, so it'll be just open all day. Make sure you do it before midnight, but I just want to do one more thing in the last couple minutes here. And we want to look at what a dV would be, a differential of volume for spherical coordinate triple integrals, which we'll do next time. So at this point, we want to, according to the coordinates for spherical coordinates, I want to draw a little dV. Okay, that looks good. And so we want, so dV is still going to be length times width times height. It's still the volume of a rectangular prism. But we know with d theta, with these differential of angle measure, those aren't lengths, right? So we got to adjust for those. So first of all, so we know we have d rho and is going to be involved, and d theta and d phi. So one of those is a length. Which one of those is a length, actually? It's all ready to go as a length. D rho. And so which one is d rho? Exhibit A, exhibit B, or exhibit C? D rho.
A.
A. It's this one right here, right? It's a little differential in distance from the origin. So we'll call that the length of this thing. 1 down, 2 to go. Okay? What about this right here? Is this d theta or d phi?
I think it's phi.
We got 1 vote for d phi.
Yeah, d phi.
D phi, right? It's a little change or variation in sweeping down from the x-axis. Okay, and we know this distance is rho, so what is that little dimension there as a length? We know it's not d phi. Remember how we got the dimension given the angle?
It's rho d phi?
Yeah, the radius, right? So you multiply your differential and angle times the radius, and that gives you that little arc length. So I'll call that the height of this thing. I'll call that the height. That's going to be my rho d phi. Finally, width is going to be, what? This back here. This dimension is d what?
Theta.
That's d theta. And what radius is that away?
the R.
Yeah, that's the R, right? Just like cylindrical or polar coordinates. So here's my d theta projected down, and that's based on a distance away of r, right? So that's my r d theta. But r is not a spherical coordinate. So what is r in spherical coordinates?
Cosine phi.
Rho cosine phi? No, I think it's rho sine, isn't it? That's
I
what
remember
that's what we should have gotten for r. Was rho sine phi? Is that right?
Yes.
On the previous page. But rho is fine. So rho d phi. So here's my dv. So I'm going to have rho sine phi is equal to r from the r d theta, and then I got another rho. So I'm going to get rho squared, rho times rho, sine phi, d rho, d theta, d phi. So that's going to be my differential in volume that we're going to use for spherical coordinates. What I needed to get these in actual lengths, right? So I'm multiplying by the radius to get these little differentials in actual length, so I could do length times width times height to get the little dv. So r d theta, rho d phi, and then we change r into spherical coordinates. That gives us rho squared sine phi d rho d theta d phi. It's going to be my differential in volume for spherical coordinates, and we're ready to write some spherical triple integrals now.